So, hello everyone. Let me just check if everything is fine now. Just a second. Okay, right. Yeah, please let
Everything
me know
is
if
fine
audio
now.
is and video is
Just
right.
a second.
Okay, so there was a slight glitch in the stream. So I'm going to start this thing from the C2 again.
Okay, right.
Yeah, please let
Everything
me know
is
if
fine
audio
now.
is and video is
Just
right.
a second.
Okay, so there was a slight glitch in the yeah.
Slight
So
glitch
we were
in
discussing
the
about the C2
stream.
and
So
okay, just a second. Sorry.
I'm going to
Let
start
me
this
just
thing from the C.
let me just remove this thing. I'm really sorry for this thing. Okay, so we were talking about C2, and we in the C2 we talked about the contribution technique. Sorry, the contribution technique, and the other thing is the sub-array formula. You can say sub-array formula. Now these are only the two things that were required to solve the C2, and it was that much easy, right? So what you do is that let's say, but for this the prerequisite is you must know the C1. The approach I used in this video, like just if you don't have watched the C1, please see this first. So let's say if the array is something like this, 3, then again 1, then again 2, 2, 3, and 3, 2, 4, something like that. So what we do is that let for some element you see the contribution of this in the answer, right? Answer is just the sum of all subarrays, uh, the minimum operation for all of the subarrays, right? Something like that. So we just go to this 2 and we ask that how much it contributes, right? So let's say if the subarray was like 2, 3, 3, 2, 4, then we know that this 2 is adding 1 into the answer, right? Because this 2 cannot be made from the array, from the operations. So this is in this subarray it will contribute 1. But in this subarray, this 2 will not contribute anything, like because it can just made by this with 0 operations, 1 operation and 0 cost, right? So that's it. So the from the C2 the different thing was only that you will see the left this one, right? The rightmost one which is in left of 2, you will find this, and if this is valid, right? If you can make this 2 from this one, if you can make, then if you can make this thing like this thing is like this 2 from this one, so then we know that in the subarrays, in such subarrays that this 1 and this 2 both comes, the contribution is the cost for this 2 is going to be 0, right? Because in any element such that this 1 and this 2 both comes, right? Let's say the subarray is like 1, 2, 2, 3. We know that this 2 is going to be made by this one, right? So that's it. If they both comes in subarray, some array, then the cost will be 0. Cost is equal to 0. And if only two comes, not one, then we know that the cost is going to be 1. So for you will count the number of subarrays like that, number of subarrays of this type, and you will just add it into the answer, right? So that was the thing, but yeah, for that you must know the logic for C1 as I discussed. That's it, right? We discussed how we find the leftmost point, but instead of the value, we also want to know the index of it, and how you are going to find this thing. Number of such subarrays such that the 2 is there, but not 1, not this one. So this is nothing but all subarray that contain a 2 minus subarray that contain both 1 and 2, both 1 and 2. You know the answer for this, we know the answer for this, and that's it. So like in the C1, we only did answer 1 1 plus plus, but in this C2 we will just do this thing. The code is going to be same. That's the only thing, right? That's how easy the C2 is going to be. Okay, so what I did is this. Like this is just similar as C1, right? All similar as C1. But in the starting, I have added this I plus 1 into n minus y. What is this thing? So this thing is nothing but this is I plus 1, and this is nothing but I plus 1 minus 1, right? As we discussed in the formula here, where is the formula? Right here. Let's say just the 3 is there, so the options are this into this, which is I into n minus I plus 1, if we talk about one based indexing. So that's it. So I have just added this case, right, that contain that element. Now I have to do the minus this stuff. So this is the same as C1. Everything is same as C1. In this I found the element index of this previous. So after that I just do this minus. This is also the subarray sum. Now what is the subarray sum? What is the case? So let's say my element is something like this, A5. This is the A4. Currently I am at this fourth value and I want to find the contribution of this one. And I find that this A2 can be made from this A4. If you just say more carefully, this is the case, right? A4 is 5. So for this 3, this, so now I want to find the number of subarrays that both are there, right? So this is nothing but this into this 2, which is nothing but this previous in the 1 based indexing, and this is nothing but n minus I plus 1, again in the 1 based indexing. So if we are going to talk about 0 based, then this plus 1 and minus 1 are going to be cancelled out. That's it. So that's what I did. So I first added this stuff and removed the other case, and that's it. So that was the only change from A1 and A2, right? And like that's how easy the C2 was, if you understand the C1 more carefully, right? Okay, so like I hope that if you understood the C1, this thing should not be hard to you. That's it. Like, and we use the contribution technique, and so for each iterate at every element and find that how much this contributes. And also we found that if the previous is also in the array and the current one is also in the array, it doesn't contribute, right? So we just added first all of the sum of the subarrays in which the current value comes minus the subarrays in which the value don't contribute, something like that. So that's it in the C2. Now we come to the like the hardest question of the current video, which is D1, but it was D, which is, but you find that it is not that tough. So this is recollect numbers, and it is also the a famous game, right? You can, like many of you have played it. So in this, we have given the 2n cards with the numbers 1, 1, 2, 2, n. Write on them, in other words, j is equal to 1 to n and exactly 2 cards for some every number. This is a card flipping game. Initially, all 2n cards are placed on back. In each turn, you flip exactly 2 cards. Then if the both are same number, we discard the card. Otherwise, you flip the original position. So, okay, this is a like lengthy, but I let me just explain this. And the n and k are till 1e5 and 1e6, right? Okay, so in this game, what is given is that what is given is that so this is a card game type of thing, right? And all of the cards initially are put on their backside. So let's say the card are something like this: 2, 1, 3, 1, 2, 3, 4, 4, something like this. So now our player start from this thing, and what it does is first he will just open the leftmost card, which is he has not opened in any move, right? So he will see this two. He will see this two. Now after that he will see this one. He will flip that both cards, right? He will see that okay, this card is two, this card is one. If they both are same, then they both are going to be deleted, right? We will just put them in one side. But okay, if that is not the case, we will again flip them back on their backside, so we can't see them also, right? But we have remembered that this card was 2, right? We have just exploded. We also remembered that this card was 3. Now, let's say we just explore the other cards, right? So we will, in the next turn, I will open, so this both card are now on their backside. Now, I will select the leftmost card, which is not explored, which is 3. After that, I will see this one card. I will see the value and I will see that, oh, this is 1. I will try to remember that did I see the 1 in some way, and I have seen the 1, right? But yeah, this move is ended, right? I have opened the 2 cards. So now I have explored this 4 cards, right? I know the value of all of them. And I remember that I know the values of the this one and this one. So in the third move, what I will do is that I will select this both and I will just remove them. That's it. So like after that, I select this two on my first turn, and I will remove. I will know that I have just seen the two in some previous moves, right? So I will remember it and just cut it. That's how this is going to be work. So let me just read it like in detail. Okay, so what is the thing is that if two cards are same number, we discard them. Otherwise, I just flip them back to the original position, and we the game play the game until the 2n cards are described, right? And we don't have to flip the two cards simultaneously. I will flip the first one and then greedily choose what is the second one card. So if there are two cards that you have flipped previously and have the same number, I will flip that two cards and just discard them. Else, I will just flip the first card that I have never flipped so far in the first one, right? That I don't know the value of. So the value is X. Now, if there is another card which also has the value X and I have exploded, I know the value, I know the index. So I will again flip that one card. So they both are XX and now this both card are discarded. Otherwise, I will flip the first card that I have not flipped. And this is the strategy is going to be. And we have given the and k, and we want to find the orientation of 2n cards. such that by this algorithms, it will take exactly k turns to just win the game. And the win the game meaning that all the cards are discarded in exactly k turns. That's it. Let's say this is the case, right? 2-1-2-1. So what will happen in this case? This is 2-1-2-1. 2-1-2-1. So what will happen is that again in the start I have never explored any card, so I will just choose the leftmost card which is not flipped, this two. So now I will ask that did I see the other two? Like did have I explored the other two? I have not. So then I will just put the second second unflipped card, like second unexplored card. This both are flipped. I have seen the value. I have remembered that at the first index. Okay, let me write it something like this, right? So I know that at the first index there is 2, at the second index there is 1. After that, I will flip them back, but that doesn't matter. I know the values now. After that, I flip another card. I flip another card. That is 2. So in my mind, I will ask that did I explore the 2 already? And yes, I have seen the other 2, which is at the index 1. So now I will flip this card. Now both are same, so both are going to be deleted. This is the thing, right? Both cards are going to be discarded. After that, I will select this one. I know that I have seen this one here. So this one. So that's how it is going to take 3 moves exactly, right? And that's how we want to answer some orientation of that card so that it takes exactly k turns. Exactly k turns. That's it we want. So in this type of question, what you have to find in initially is that what you have to think is that what is the min k and max k possible. So this is the thing you have to ask. Okay, what is the min k and what is the max k? So let's say max k is kind of tough. What is the min k? So the best way is just like something cards or something like that. You just take this one, take this one, both are discarded. This and this both are discarded. This and another is this, both are discarded. So this thing is done in 4 moves for n is equal to 4, right? So we can say that minimum min k is equal to n, right? This is the one thing. Right. Now, what the max value of k can be, like you have to find some algorithm, something like that. So, what is the best case? So, like we can think of something storing the elements like this. So, in this, what is going to be happen is that in the first we will explore this two, then explore this two, then explore this one, and I will remember that I have seen this one, right? So, instead of flipping the next element, I will flip this one and discard both. I go to this, discard both. I open this, I know that 3 is there, discard both. I go at this, discard both. So the number of turns are going to be like the 2 to explore them plus this 4, which is 6. Okay, so this approach is also kind of like fine, this is okay. But is there any other approach, other better approach, right? Like, and how you are going to find the better approach? Just take the random test case and try to make it like better. So while solving this, the observation I got is that something when the case are something like this, something like that. So I know, like in one move, I explore the first one. Then if I know, I see this one, I see 3-1. And then I remember that, oh, this one is I have seen, but this is the second one, right? Now this one move is done. So there is one and two moves are done. And in the third move, I will flip them both, right? This is the best case that I have made, right? This is the best case. Why? Because it takes one move to explore the first one. It takes one move to explore the other one. Well, yeah, that's true that the other three and two are also being explored, but like just forget them for a minute. But right, can you just see this way? Can you just see that let's say when this one was case, like one case, the both one are just explored and discarded in one move. When the case was something like this, sorry, when the case was something like this, sorry for this thing, I don't know. Okay, 1 2 1 2. When this was the case, it takes one operation to explore the first one. But in the second operation, I will just explore it again and also flip the both, right? So it takes only two operations. But in this type of move, it takes one operation to explore the first one. The other operation, I will explore this one, and then I will remember, oh, that I have flipped the two elements that are same. I know the index of them, so I will just flip them. So this takes three moves, and this is the best case. So that's how I just have to find some algorithm of something like that. Okay, so can you all understood this thing? This D. So like it is tough to uh, have this observation, but if you just like think this type of systematically, like for some, let's say for some both I or both are X, then what is the max value? What is the like maximum operation you can just have for to find the X, right? That's what I thought in this case. So this is the case. So now from this, we have to like think of some algorithm. Some algorithm. Okay, so let's say I have five elements. I put one here, I put two here, three here, and one here. So that I know that this will take. So now, if I put two here, I know that this two will be explored, this two will be explored, and then after that, in the third move, this one and one will be deleted. And after that, after this third move, this two will be explored and it will be cut down with this two. But I don't want that, right? This is, I don't want this thing. So what can I do is I will put some dummy variable here. Let's say I put 5 here and then put 2 here. So after that, the three operations are going to explore this thing. In the fourth operation, I will explore this one, and now I will remember that, oh, this 2 is already explored. So this is third, this is the fourth operation, and in the fifth operation, I will delete them. That's it, right? Because if the 2 was here, it will take only like it will take lesser operation to discard the two, both twos, right? But I know that for that I have to put some dummy variable here. So after that, like let's say I want to make a 3, I have to make some dummy variable here. But if I put 5 here, I know that 5 is going to be cut here. So I don't want 5. I want some dummy variable that is not explored yet. Not even a single one, right? So like let 4 is not explored. I can put 4 here. After that, I know that 4 and 5 are only remaining, so that doesn't matter. So this is the maximum. So what is the answer in this type of case? Let me think in this type of case. So one operation, two operation, then third operation to discard them both, fourth operation, fifth operation to discard them both, then sixth operation, seventh operation to discard 3, 8th operation, but in the starting I will take this 4. I will remove this. I will remove this. And this is the 9th operation. So it take 9 operation. For 4, if you take n is equal to 4, the answer is going to be 7. So that's how I got that max is equal to 2n minus 1. That's it. So that's how we have found that min and max, right? Max k we have. This is the values of k. Now the another question is, what if we want some values in between this n and 2n minus 1, between min and max? Then what will be the case? Like, let's say you want k is equal to n plus 1 or n plus 2. How you are going to make it? And can you make it? So, if you just take some test cases and think intuitively, you find that this all are correct. You can find all of the elements from this n to n minus 1. But now the only problem is to think how you are going to make this orientation, right? We have already discussed about orientation when the k is equal to n and when k is equal to n minus 1. That's it. So this is easier. This is very simple. The thing is, you will just do this operation, like do this type of orientation, do this max orientation, uh, and like, okay, so what you know is that we will find that what are the extra you want. Extra is nothing but k minus n, right? What are the extra you want? Extra moves. So we have think that initially all the elements are just explored in one move only, or just discarded in one move. It's something like that. Something like that. Right. The both are just, for this k is equal to 3, which is equal to n. So, but what are the extra steps I have to do? And this, for this extra steps, I have to think, right? So this is a easier one. Let's say I want n plus 1, and let's just think when n is equal to 4, k is equal to 4, 5, 6, and 7, all 4 cases. And that's how, if you just find a solution on this test case, we will have some pattern, right? So this is the way to think in this type of question. The first thing we have to think is about minimum and maximum, and after that we have found this, we will think about how to make the middle values of k. So this is like a famous type of questions, right? Recently I have seen it in the IICPC prelims ones, the E one, if you remember. So when k is equal to 4, this is easy. We will just do this test, right? Now when k is equal to 5, so what if I just do this 1 to here? And I know that now this thing only is added plus 1 to my operation, right? This is just plus 1. One operation is wasted to explore this 1 and 2. So after that, I just put all of them are same, right? In this, you will see that k is equal to 5, right? Because the one operation to just explode, and then all of the four operation will discard 1 to 4 all of the things. Then what if the k is equal to 6? Then you can have something like 1, 2, and this max type of thing, right? We will just have the the operation to discard 1 should be equal to 3, right? How we discussed. This pattern was this thing, right? If you remember this thing. In this one, we will explore the first one, then explore the second one, and then waste a move to discard the both values. That's what we can do. And so this thing only is done plus 2. And after that, I can just do whatever the same thing, right? If the k is equal to 7, what I will do is set 1, 2, 3. Sorry, I just forgot about 4 here. 1 2 3 1. Then I will also do that thing we discussed in this max logic. I will also like put this 4 and 2 here, and then just 3 4, right? So that for this one it is done the plus 3. This one is also done plus 1. Sorry, plus 2. This done plus 2, right? Just, and when you just see the answer for this, when you count the answer, the key is going to be 7. That's it. So this is easier. So we just, like we did here, we will just print 1 to here. This is just plus 1. Then every this case are doing plus 1 here, right? Can you understand or not? Right. Let's say, just see here. Like this is also plus 1, and this thing was also done plus 1 to my answer. Then I have just used the simplest approach. I mean the approach to make the like to solve I mean to win the game in the as fast as possible, right? I will just put this together with all of them. So if there was like 6, I will just put this something like this. So that's it. So first I try to maximize the answer until I come at k, and after that I only do this add operation. That's it. So this was a very easy case, and let's see the answer for this case. Where is the code? The code is very easy, and let's see it here. Okay, I guess there is some problem to open this code. In the first one, I just forget about the case when k is equal to n. Right, I just have to print the. Okay, this is recollect numbers. So, like just give me a second. I have to find this thing. Yeah, this is the. Okay. Uh, well, just a second. Yeah, this is the code. This is it. So, yeah, the case also. Yeah, I forgot another thing also to think. How we are going to print this stuff. So, I know that when I have to add something, right? When I have to add some answer, I know I have to find this dummy one. What is this dummy one? So this element is nothing but the one the one which is never exploded yet, which is never flipped, right? So like both fours are never explode, right? I don't know the index of any of this four, and this two is just going to be the index which is explode exactly one time. Exactly one time. Ah, shit. Alright, just a second. I don't know what's the mistake. Explode exactly one time. So this is the both thing. These are the two things I have to consider, right? So that's it. So I just have to decide the both case. If the k is less than n or greater than this thing, then the answer is just no. If the k is equal to n, maybe I could solve it in the. But I just think that it would be better if I just solve it here. If k is equal to s, okay. So in the one wrong answer I got, I forgot to print yes here, and I will just forget like 1 1 2 2 3 3 4 4 type of sequence and return it. But else, what is the case? Now comes the main part. I will find how much I extra need, right? This is k minus n. How much I extra need, because I know that all of the things from 1 to n will have one operation, right? At least one operation, right? So all of the things from 1 to n will take at least one move. So I know that the n moves are, you can say, for to just discard, right? But now I want the extra moves. That's what I do here, which is k minus n. Now, this p out and this p baki, what are this thing? This p out is the leftmost, the smallest value, which is for which one frequency, I mean the one occurrence I know, and the other occurrence I don't know. I have not explored yet. And this p baki is just remaining. Right? Both of the values are remaining to explore. That's it. In the starting, I add 1, 2, and I know that doing this operation, this is just extra operation. I did need minus minus until this need is greater than 0. What I do is I add this. So this is the dummy thing we talked. Then we add this thing. So now we just add them. We just move the pointer and do need minus minus. After that, okay. So what is the approach? Let me just take it by one example. Let's say I want 5 and let's say 6, and the other thing is 10. Okay, so now first I will check if this 10 is range. So the range for 6 is going to be 6 to 11. So this 10 is in the range. So yeah, answer is possible. So after that, what I do is that I will count the need. I mean, how much extra I need. So 10 minus 6 is 4. I need 4 extra. I will add this 1 2 in the starting. I know that the I this doing this thing only adds one to my answer. So this need is now lesser, subtracted by 1. After that, I know that here I have to put some dummy thing which is not explored yet, and I have to put there which the element which is explode exactly once. So yeah, explode exactly one thing is this one, and dummy thing is this 3. Like if this is 6, we can put 3, 4, 5, and 6, all of them, right? We have done this operation only, explode 1 and 2 only. So we can put any of this, but yeah, for simplicity, we just put the smallest. So I put the 3 here and the 1 here. Then doing this operation, my need is also reduced by 1. After that also, I will put some dummy here. So now my dummy is 4. My explode exactly one thing is now 2. So this thing also I have reduced this to 1. Again I will do this. I will add some dummy. I will add some here. This will make my 0, and until I have 0. So all of the elements that are explode exactly once, I will just put the other here, right? So that what will happen is that I have just let's say I have explode all of this. I go to this 4, just remove it in one move exactly. I go to this 5, remove it in one move exactly. And all of the bigger values that are not explode, at least one, right? Not explode. I will just put pair of them, something like that. This is the case. So I will put the bunch of elements exactly which are explode exactly once, and then after that bunch of elements which are not explode. So that's it. That's what I do, and that's what how easy this question was. This thing is already done. So now this p out less than p baki shows me the number of element which is explode exactly once, and I'll just print them. And from this baki to n, I know that this element are not yet explode at least once also. They are not yet explode. So I put the pair of these two. and then just to p baki baki, and that's it. So let's try to see the answer, right? Let's say the n is equal to 6 and the value is equal to 8, we say. Okay. Yeah. So this one too is compulsory, right? As we did here. Now we just put this 3 one here. And we knew that after doing this thing only, we have done our work, right? Doing this thing only, or this for operation, we know that we will reach our the expected state. We don't want to do another extra operation, but yeah. So that I will just put the bunch of elements which are explored at least once, and then the bunch of elements that are not explored. So all of this case, all of these elements are just going to be discarded in one element, one move. So that was it in the D question. Okay, so that was it for the contest today. Like this, A2, B2 were not that easy, and also like you can say this were anti-EI type of question which are like tough. You can't prove them easily. This C1 was a nice C1 was my favorite question. C2 was just the one you can say 1 2 line difference, right? You just have to add one formula in this. And D was very easy. I don't know why people like were not able to do the D. But yeah, the approach in D was like quite hard, but the code was like very easy. Like there is no data structure used other than the vector in this code. So that was it in the contest. Just like give me the feedback, like how the contest was to you. And I guess that was it for today. So